Well, good afternoon. Again, thank you, Sissy, and the organizers for asking me to present some discussions or some talks on liquefaction effects on buildings and facilities, some of the lessons learned from New Zealand. And it has been a very collaborative exercise. We almost speak the same language. I can almost speak Kiwi now. I can almost understand Brendan when he talks really fast. But we could not have done this without Brendan, without Mishko Chubanowski, without the rest of the people, both engineers and researchers, sharing knowledge and sharing data. And of course, the National Science Foundation and their support, as well as some of the New Zealand agencies, were critical. It was just amazing to see the widespread liquefaction and, very importantly, its effects on infrastructures. It reminded me that liquefaction is not just a soil event, it's a water event. And in fact, there was flooding, such as you saw here. And so these houses not only had damage from deformation, they had damage due to water and sand. When your toilet doesn't work, life is not good. And there were important issues in terms of the office buildings in the central business district. There was an area that had pervasive liquefaction from the 2011 Christchurch earthquake, and we saw tall buildings, even buildings that were 11, even one building that was 21 stories tall, have ground that softened and allowed the building to basically tilt, and that was one of the reasons why the buildings were taken down. When we talk about liquefaction effects, the geotechnical engineers in the room realize that we have this empirical method where we use the demand is the cyclic stress ratio, the capacity is what separates between liquefaction effects being observed at the ground surface to where we have no liquefaction, so that transition line is called the CRR, the cyclic resistance ratio, and in the simple world, factor of safety is the resistance or capacity divided by the demand. What's misleading is we calculate factors of safety, and in this region we could calculate a case where this is our demand, that's our resistance, a factor of safety of 1.2. In this area we calculate demand and the resistance, we have a factor of safety of 1.2. That might lead you, same factor of safety, same effects. But it's very important that liquefaction is not the same on the left side of this curve as it is on the right side. When we get to the low penetration resistance, notice that the backdrop I have strains. We don't want to just talk about liquefaction triggering because that's one thing. We want to talk about the consequences or the effects of liquefaction. And you can see that here you go from very small strains on the order of 1% to very large strains with small changes in resistance or small changes in demand. That should make us all very nervous. That is a brittle failure, and being a little bit off in our demand or resistance calculation can be the difference between having no damage to having severe damage. This is an area where we can get progressively more strains, but it's more of a gentle hill, and therefore the consequences are different. So even though we call it all liquefaction, I think that's one of the mistakes that we've made as geotechnical engineers. We really should call this flow liquefaction, or the potential for large deformations, whereas this is cyclic mobility with limited strain potential. They're different animals. One of the very important lessons from Christchurch was the most valuable tool was the cone penetration test. It was nearly continuous, giving us this true look of what this fluvial environment looked like. And if we're able to catch that at a building scale, we have to have a cone penetration test. They have done now over 22,000 cone tests since the Christchurch earthquake, because that is the most reliable way in sandy and silty materials and even some clay materials to characterize the ground. One of the arguments about using the cone is, well, I can't advance it through dense gravels or slightly cemented soils, and that's not true. Using the Kiwi ingenuity, they came up with a collaring system where when we hit ground that we had not been able to get the cone through back in July, with this new device, we were able to essentially use a dummy cone, vibrate through the dense gravel. Once we saw it started to loosen up, we could go back, pull the dummy cone out, put the real cone in, and get there. And so there's no reason for not using a cone penetration test in today's world. The standard penetration test, which name is really the not so standard, I don't know what it is test, should not be used by geotechnical engineers in the year 2017 or in the future. This great test that was invented 100 years ago has served us well. It's not the best tool to be used. For example, I and designers in Christchurch have not used any of the SPT data because we don't know what N means. We don't have energy measurements. We don't know exactly how they did the test. The only test that's been reliable for us as researchers and as consulting engineers has been the cone penetration test. In terms of capturing liquefaction effects, the Japanese have been looking at this and saying it's not just that you have liquefaction, it's the effects of liquefaction. So the idea here by Iwasaki was to say, let's integrate the factor, 1 minus the factor of safety. So the lower the factor of safety, the worse things should be. And let's use a weighting function that weights the shallow liquefaction more heavily than the lower liquefaction. It's a linear scaling. Well, Sjoerd van Balagoy, working with Tom O'Rourke, myself, Miško Čubanovski, and others, developed something called the liquefaction severity number, which has two important things. Instead of just focusing on factor of safety, which is an on-off switch, black and white, he's looking at a consequence, strain, and then he's using a 1 over z, so it's basically an exponential decay, really weighting shallow liquefaction, because Christchurch taught us shallow liquefaction, the liquefaction right beneath your feet is the most important liquefaction. If we look at one of the ways we calculate liquefaction effects, it's with this kind of curve, where we have, as we go to decreasing factors of safety, we get increasing volumetric strain. But notice it's not just a function of factor of safety, it's a function of relative density. You have soils that are relatively dense, they can liquefy, they can have low factors of safety, but the strains are much lower than a soil that has low relative density, a very loose sand, for example. If I just flip that over, I can sit there and say, decreasing factor of safety for a soil deposit is because the peak ground acceleration is increasing. So when we go from the Darfield event, which had moderate accelerations, to the Christchurch event, which had severe high accelerations, we're getting a decreasing factor of safety. But it's not just factor of safety, it's also relative density. As you go to decreasing relative density, we go to increasing volumetric strain. So I see this as an improved tool to classify liquefaction effects. And one of the things that we see from this tool, the dotted line is LPI, which is essentially saying whether it's 0.2G, 0.3G, 0.5G, 0.6G, it's almost a linear increase. And that's not what we see. You have no effects of liquefaction. You get liquefaction, which is a brittle phenomenon. And then whether you get 0.4, 0.5, or 0.6G doesn't matter. You have massive liquefaction, you have massive liquefaction. So this is a better tool for looking at liquefaction effects. And so, for example, this is some work done by Sjoerd van Balagoy from Tonkin and Taylor. The hot colors are where he, using the cone penetration test and his liquefaction severity number, says there should be severe effects of liquefaction. And that's what was observed. That's what he's estimating, and that's what was observed. So you could say that that's a tool that you could use in a place like New York to do some regional planning to get a sense of where you might have your more severe liquefaction issues. Now, one of the things you might notice if you're caught this is an area where our techniques, mainly because of the liquefaction procedures we use, said there should be significant problems, but they really weren't. And so you focus first on areas where there's high damage, but then you want to go back when people are being asked to spend hundreds of thousands of dollars to remediate ground. Should they be doing that? Well, our procedures are saying there should have been a problem, and often there was not. So this is just one of the sites in the southwest part of the city where this area was strongly shaken by 5 earthquakes. In one case, the ground shaking was 0.4 G, and there was no liquefaction ever observed. Yet our simplified methods say we should have seen liquefaction there. Are we going to ask this owner, because our methods say there was supposed to be liquefaction to invest hundreds of thousands of dollars to remediate the ground, improve their foundation. No, we should be listening to case histories and the field data and wonder why our methods are overly conservative. When we look at the methods, again, any triggering technique, this ended up being using the Robertson and Ride, but whether you use the Boulanger and Idris or whether you use the seed method, we calculate low resistances from our penetration resistances. We have high demand, so therefore the factor of safety in these layers is uniformly down around 0.5. We calculate large strains that we integrate. We estimate nearly 6 inches of settlement. We get a high LSN number. Our techniques are saying it's a problem, but we have observations that it's not a problem. And in fact, if we look at several cones, and this is very simple. This is the cone penetration resistance over the upper 10 meters versus, and then this is I sub C, a soil behavior type index, which tells us how the soil responds over the upper 10 meters. The only difference between these traces are the red are sites where ejecta and ground failure was observed, and the blue are sites where there was no ejecta. All of these sites, by our methods, would be predicted to have massive liquefaction issues, yet the red sites had massive liquefaction issues, but the blue sites did not. And when you look at that, you don't really see it in the cone penetration resistance. If you correct these for fines content, you'd get them up around here. You have similar types of tip resistances. What you really see here is that all of these red cases are uniformly thick deposits of clean sand. And you realize liquefaction is not an element. It's a deposit with water communicating to each other that we get major problems. So that's what we're missing when we just look at individual layering. We're missing the fact that a thick layer that's able to move its water very rapidly throughout that entire layer can have a lot of ejecta, whereas if we have a bunch of thin layers that are disconnected, it's like having individual pipes that are not connected, and so we don't get that major ejecta. In fact, it's all about geology. If we go back and recognize Christchurch was largely developed because of the gold rush and other types of people moving there about 150 years ago. And so if you go back and look at photographs in 1880, that's what Christchurch looked like. In 1819, they basically started in the area that had the shallow gravels. That's where you would start, and that's where you build your cathedral. And then you would move out into the poorer ground. But the poorer ground is got low penetration resistances, but it's highly layered. And you might have soils that might liquefy, but they're surrounded by soils that won't liquefy, and we don't have this communication. And so it shows really the importance of not just relying on the cone, but maybe moving to continuous sampling and actually doing geologic mapping of the samples to really look at the geology and understanding it. In fact, that's something that plays importantly here in New York, is there's cases where you get varved materials that have this interlaying, that have low penetration resistances, but then you say, will they actually have significant effects from liquefaction? They might have liquefaction at certain layers, but it's not going to be the same disastrous effects that you had from like a uniform clean sand material. And in fact, it really points to the purpose of laboratory testing. This is from a project where initially the tip resistances from the cone and the SPTs that were done suggested you had a resistance down here. This is the demand, so you had a potential of severe liquefaction and consequences. But after testing this material, because they also had an overconsolidation ratio, so that made it more resistant, the laboratory testing suggested the strengths were about twice as high. And so I think there should be a renaissance in reconnaissance, like Ellen mentioned, but there should be a renaissance in laboratory testing. Another important thing is we geotechnical engineers focus a lot on fines content. Fines content happens to be the percent passing the 200 sieve. And I remind myself that soil doesn't know there's a 200 sieve. If I have a soil that is a very fine sand that's uniform, made of quartz, or a very coarse silt made of quartz, it doesn't act any differently. And so I think there's been an over-reliance in our profession on simple things like fines content, where in some cases, maybe for a well-graded material that might matter, but for uniformly graded very fine sand and very coarse silt, it doesn't matter. The other thing I think is it's brought me back into looking at soil. As much as we get high tech, I sometimes forget to look at the soil. And when you take this material and you look at it, you realize, okay, this is different than a rounded sand that might actually liquefy and flow. This is a material that actually is very angular. And so if it softens, when you start to push it, it's going to lock up because it's a very angular material. It's very dilative. And so looking at soil and the geologic detailing, there are ways of basically couching judgment or adding judgment to our analytical techniques so that we're not bound by them, or we have ways of explaining why they might be overly conservative. Structural engineers always talk about liquefaction being bad for their buildings. Buildings are bad for soil. Here's a case. This entire town of 1 to 2 story buildings had no evidence of liquefaction. They decided to build a new regional hospital that's 5 to 6 stories tall, and that's the place they had liquefaction. In fact, this regional hospital was put out of commission, and they were using a tent hospital to care for people after the 2010 Chile earthquake. Because of the heavier load, it put in inertia forces which caused higher strains and deformation. So when you put a building out of site, realize that you're potentially putting more demand on that site. In terms of what liquefaction does to buildings, this is a good example from the Tohoku earthquake where we have a pile-supported building that did not move down. Then this is liquefaction of the hydraulic fill, and everything went down 30 centimeters. But what this building cares most about is, yes, it went down 30 centimeters because the ground went down 30 centimeters, but it went down 40 more centimeters because this punched in because of the shear deformation. So it's not just volumetric reconsolidation, but we also get shear-induced deformation because of this shallow building on a mat, putting that in. So the total amount of settlement was actually 70 centimeters. So when we look at displacement mechanisms, never forget that the most important mechanism is ejecta. If you get 6 to 12 inches of sand on top of the ground that used to be beneath your foundation, that's not good. Then the second most important problem for buildings that are significant, so your multi-story buildings that have inertia, have mass, is actually the fact that the ground softens, and that can actually cause the building to punch into it. And then as the building is rocking back and forth, it's doing a cruel thing to the soil. It's pulling on the soil and then hitting it, pulling it and hitting it. And that action allows it to work its way into the soil more actively. We call that SSI ratcheting. And then last and least, for most cases with buildings, is volumetric deformation, which should be considered, but is often the third most important thing. The positive is with advanced analysis, we can do a good job and we can capture these effects. If we understand the ground motion, if we understand the site, if we've calibrated a numerical model to be able to handle this type of loading, we can get calculated differential settlements which affect the structure, which are very close to what's measured. If. And of all those ifs, good analysis couched by good laboratory testing depends on excellent sampling. If we're going to invest the time in doing advanced analysis to gain important insights for important structures, we need to invest the time and care to do the best possible sampling. Bad samples and bad testing will lead to bad analysis. So in conclusions, I think that this sequence of earthquakes taught us that these loose, shallow sands and the non-plastic shallow sands, the silty sands and the silts, they led to much of the damage. And much of it was because of ejecta. And so that's the most important thing to focus on. However, on the positive side, there were areas where we had low penetration resistances. Our cone penetration testing, SPT testing would suggest that this was going to be a problem. Our simplified methods that have been validated by a number of case histories would suggest this would be a problem. However, there was no liquefaction, even if severely shaken. And that really points us to the way to get out of that is to do sampling and both map it geologically, to look at the geologic details, understand the depositional history, but then also to test it to get better resistances so that you don't have to rely just on the simplified method. And we can sample fine-grained materials. Can't sample sands easily, but we could sample fine-grained materials, or silty sands in case. When we look at building performance, consider shear-induced deformation and ejecta, because those are critically important. Don't just look at techniques that are based on free field volumetric strains, because you're missing the most important things. And there's a paper that I'm fond of, because I guess I wrote it, published in 2017, Soil Dynamics and Earthquake Engineering, that gives you a simplified method of dealing with it. A lot of it depends on engineering judgment and case histories. Analysis can only take us so far. And last but not least is, as the New York Code and others have relied on ASC 710, and they've moved to an MCE ground shaking level, which is 1.5 times what the ground shaking level was before, we often calculate liquefaction at sites that just before we didn't calculate liquefaction. I think it's important to remember that what we care about in terms of the MCE level, that 2% 50-year ground motion, that's very rare earthquake, is we care about life safety. And so we don't need to worry about maybe 6 to 12 inches of settlement if the structure is built well. And one thing we learned from Christchurch and also from the Japanese, a well-built foundation that ties everything together is worth its weight in gold. And we should also look at the lower levels of acceleration and look at consequences and how that might affect the performance of the structure. But in the MCE level, it really is a life safety issue for foundation engineers. Thank you.